Welcome back. Now we'll try another problem from 2.1. This is application number 1, the logistic equation, or logistic growth model. So this one's interesting because 1, we have different letters to work with, and 2, we have parameters as well as variables. So dp dt determines the independent variable and dependent variable, which leaves us with parameters r and n. This happens to be the growth rate, the exponential growth rate at the beginning, and then the carrying capacity we'll talk about later. We also have an initial condition to work with. So first let's check to see that it is separable. We can use our method on it. So I have it in slope form already. Let me separate that slope form. So I look for a function of t. There's no t. Well, this is tricky. But we remember that a function of t can simply be a constant. So I'm going to pull out as many constants as possible. So I pull out the r, and I'm also going to factor out a 1 over n. So r, that should be r divided by n right there. And when I factor that out, I'm left with a p and an n minus p. So I have the function of t, essentially the constant function, and the function of p, the dependent variable. So let's check. That works. So now let's separate and integrate. So p times n minus p on the bottom. On the other side, we have r over n times dt, and we integrate both sides. On the left-hand side, we need to use a method from Calc 2 called partial fraction decomposition to break that divisor up into components. Partial fraction decomposition. So the goal is to break up our common denominator into separate denominators. So we have our 1 over p times n minus p equaling an unknown constant over the first product plus another unknown constant over the second. Now, one thing to notice here is that each of these denominators are linear terms, or they're at most first order in p, which means that the top terms must be constants or 0th order, because when we break up into partial fractions, we need to have bottom heavy fractions for this to work. Okay, to keep that in mind. So to solve this equation, I'm going to clear out by the common denominator of p times n minus p. That will give us 1 equaling a times, well, p's cancel, leaving us with n minus p, and then b times n minus p cancelings, just p. Now I can expand that out. I have an a times n, that's my constant term, and then I will have a negative ap plus a bp. Those are both multiples of p, so I'll get plus a negative a plus b. Okay, so now to solve this one equation, I look at the powers of p on both sides. Let's use green for that. First, I look at 1. What are the constants on the other side? an. Okay, so that means 1 is equal to an, or a is equal to 1 over n. Again, n is a parameter, it's a constant. Then I look at the powers of p, And there are no powers of p over here. And there's negative a plus b powers of p there, which means 0 is equal to negative a plus b. Or, if I solve, that gives me a equals b. But I know what a is already. It's 1 over n. So b also equals 1 over n. So, plugging that back into my equation, I have the integral. Well, here, let's clean it up a little bit. I have a 1 over n over p plus a 1 over n over n minus p, all multiplied by dp. And let's erase. Then our algebra. Okay, so now we can integrate out, now that we've done the algebra, to simplify it. First, I can bring in 1 over n out. Then I integrate 1 over p. That gives me natural log of absolute value of p. Then I integrate 1 over n minus p. It's a very quick u substitution. So let me write that out on the side here. If I let u equal n minus p, then du is equal to negative dp in that sense, which means that I have a negative pop out here. So the integral of 1 over n minus p dp will equal the negative integral of 1 over u, which is n minus p, du. Well, integrating 1 over u will leave me with natural log of absolute value of u. But u is n minus p, so I get a natural log of an absolute value of n minus p. That negative means I subtract the two logs. And then I will have a plus c. I'm going to send that plus c to the right-hand side. I'm going to combine together. On the right-hand side, I'll send that across. I'll have r over n times t plus c. And we'll call that just c1. It's a combined constant from the right-hand side and the left-hand side together. Now, since I have a common 1 over n, I can multiply through by n, and then also combine the logs together. So on the left, I have the log of, when we have a difference of two logs, we get a division of what's inside those logs. And since they're both an absolute value, I can bring them both inside the same absolute value. On the right-hand side, multiply by n, so I have r times t plus c1 times n. Now, c1 is an arbitrary constant, so c1 times n is a new arbitrary constant. We can play this game all day, can't we? And now I'm going to exponentiate both sides. That leaves us with p over n minus p equaling, I have an e to the rt, and I have an e to the c2. Notice I didn't write the absolute values here because I'm going to turn that uncertainty absolute values into a plus and minus on the right-hand side. And this will become my new constant. there is a solution. It's an implicit solution, which means that it is solved, we integrated all the way, but we have not yet solved for p independently. To do so, we need to multiply both sides by the denominator on this left-hand side, and then move the p's together. So if I multiply both sides by n minus p, I get n times c3 e to the rt minus p times c3 e to the rt. Then I bring the two p terms together. That gives me a 1 plus c3 e to the rt all times p equaling n. And finally, dividing by, I can solve p. So there is an explicit solution. P is equal to n times c3 times e to the rt divided by 1 plus c3 e to the rt. Now, this is not, let's say, an optimal form of that solution. The reason is we have c3 showing up in two different locations. We'd like to make it show up on only one location possible. Also, we have competing exponentials, which doesn't necessarily seem like a bad thing, but there is a way to simplify this. So, now that we solved it, I'm going to go back a little bit. And see what we can do here. Notice we have what's called a general solution. We haven't actually solved for the constants yet. So, how could we change the form? How could we simplify it? Well, to move the exponentials around, we could certainly multiply by the inverse. Now, you might think the log? Wait, no, not the log. Multiply by something that would give us a 1. So we could multiply the top by e to the minus. Oh, that's a bad color. Let's try green. We can multiply by e to the minus rt on the top and the bottom. Notice that multiplying the top and bottom the same thing gives us the same quantity. And while we're at it, we can combine the constants by division. And that will leave us with P of t is equal to, on the top we cancel the c3's, our e to the rt times e to the negative rt will give us a 1 because we end up adding the exponents. Rt minus rt is 0, e to the 0 is 1, so we get n. On the bottom, we get a 1 over c3 times e to the negative rt plus, now the c3's cancel, the exponentials cancel, plus 1. So that's an alternate. Now that's not quite the optimal, but it's close. Why is it not quite optimal? Well, we end up having a 1 over C3. Now, C3 is an arbitrary constant, so dividing by that arbitrary constant gives another arbitrary constant, except for when it's 0, of course. So we could write that as n over, as 1 plus c e to the negative rt. This is one of the standard forms for writing the logistic growth equation. It shows the carrying capacity, here is n, and then the exponential growth rate, r, right there. We have the exponential growth, e to the rt. It's on the bottom because as time increases, this component goes to 0, and we go to 1 on the bottom, and on the top, and we head towards n. But when t is near 0, e to the 0 is 1, and we get n over 1 plus c, which gives us this smaller quantity. So let's find out what that c is in relation to the initial condition, p of 0 equals p sub 0, or p naught. So, initial condition p of 0 equals, so we plug in 0 for t, n over 1 plus c. E to the 0 is 1. Should equal p naught. Now there's a number of variables here. P naught is the given parameter. C is the arbitrary constant. N is another parameter. So let's solve for C, the arbitrary constant. To do so, multiply both sides by the denominator. We get n is equal to p naught plus c p naught. Then, since we're solving for the arbitrary constant, we get p naught times c is equal to n minus p naught, or dividing by p naught, we get c is equal to n minus p naught over p naught. Now, if we combine those two things together, we get our specific solution of 1 plus n minus p naught over p naught times e to the negative rt. Now, once we put our initial condition in, we know exactly what the value is at every single time, given the parameters r and n. Now, you may be thinking, where are the numbers? Well, solving problems like this actually save us time, because what we're doing here is solving all possible logistic growth models for every value of r, every value of n, every value of p naught, so that when you actually use this differential equation, doesn't matter what initial condition you have, doesn't matter what parameter values you have the same exact formula. That's the power of working with parameters, doing multiple problems all together. Okay, that's a wrap for this one.